So the first speaker is Basile Confavreux, who's a PhD student at the Institute of Science and Technology in Austria, in Tim Vogel's lab. So he studies synaptic plasticity and predicts new rules or analyzes known rules using machine learning. So let's get started with Basile's talk.
Hi, everyone. Thank you. So yes, I'm Basile Confavreux, a PhD student with Tim Vogels at IST Austria. And previously we were at the University of Oxford. And the work I'm presenting was done in collaboration with Friedman Zenke, Everton Agnes, and Tim Lillicrap. So we developed an approach to discover new biologically plausible plasticity rules in silico. So to start with, synapse is a connection between two neurons, and synaptic plasticity is the phenomenon that describes how this connection changes over time. It's widely considered to be involved in high-level cognitive functions such as learning. And these changes can correspond to the number of individual synapses between two neurons, changes in receptor numbers, vesicle numbers, etc. So these processes are complex and not well understood, but usually we collapse all these effects into the evolution of a single scalar, the strength of a synapse or its weight. And what we are looking for in this work, the plasticity rules, are the function describing the evolution of synaptic strength over time, this delta W function here. And even by collapsing everything into a scalar, this still turns out to be a hard question, mainly because we don't have the tools to observe synapses through time without destroying the network. And there are at least 17 neuron types in the cortex alone, with over 140 connection types, each following a potentially unique plasticity rule. And the classical rules that we know today are the result of 70 years of study of only a few connection types. So at this pace, it will take hundreds of years to describe all the plasticity rules that operate in the brain. And also, these known rules don't give any interesting function to a neural network on their own. Actually, most of the time, the network blows up, as you can see on the left with this raster plot, which was simulated using a Hebbian rule. So we are still missing the link between plasticity and the higher level cognitive functions like memory. The analytical way of solving this is saying, okay, we want this network to have this function, which we can express with the cost function L. And now we solve this minimization problem and we get the optimal plasticity rule delta W star. The issue is that this top-down approach fails for analytically intractable systems, or when you are not quite sure what the exact function is. And also there's only so much biological realism that you can explicitly include in that cost function for analytical purposes. So that's where we come in and say, can we have a hybrid approach in which there is a cost function that says what we would like the network to be doing, but also an approach that would work no matter how intractable and how misbehaved our systems are, and include as much biological realism as needed. So here's what we want. A biologically plausible network with a target function or architecture. And we want to get to that network starting from a random network that has one or more plasticity rules and a bit of time to get there. And the network and target function can be anything you want, really. All we require is that you're able to give a score to the final network, a scalar loss that says how well this network is solving the task or having the right distribution of weights. And then we use black box optimization to minimize the loss with respect to the plasticity rules. And this question naturally rephrases itself using a meta-learning vocabulary, because what we have is an inner loop with some unsupervised learning with the plasticity rules, and an outer loop, which will learn the unsupervised learning rules using gradient descent or evolutionary strategies. And the paper we have at that point is a proof of principle that this approach seems to work. So that is to say, when used on setups for which we have an idea of the solutions, it finds them. And the rest of the talk will be showing 3 example setups for which we know the optimal learning rules. And yeah, please note that in these precise setups, there would be more efficient ways of finding these rules, but we were interested in the method, in calibrating these methods so that we can then test it on real life problems for which other methods would fail. So as a toy example, here is a linear feed-forward network performing principal component analysis. We know since the 80s that a linear network can have its weights converge to the first principal vector of any dataset, provided its connections evolve according to this plasticity rule named Oya's rule. So Oya's rule is a Hebbian rule, so pre times post, x times y. So this is a Hebbian term with and also a normalization term for stability. Then we have a loss assessing how far the weights after training are from the first principal vector of the input dataset. And our goal is to start from a random rule in there, and then by minimizing this loss, to recover Oya's rule. And by random rule, I mean any kind of dependency on the pre-activity, post-activity, and current weights, which we approximate using a Taylor expansion. So optimizing a plasticity rule means optimizing these A coefficients here in front of each term. So we optimize the loss with covariance matrix adaptation, which is an evolutionary strategy. And this is what we find. So each line is the evolution of one parameter of the plasticity rule across an optimization process, starting from a random initialization. You can see that all the parameters go to 0, except this blue one, which is the Hebbian term, which goes to some positive value, and the normalization term in orange, which goes to minus the other one. So that is to say, we recover Oya's rule. And this result itself has been expected since Bengio et al., like in the early 90s, who predicted that we could solve this. But say now we would like to recover additional principal vectors. So we take the same network as before, but now we add more output neurons and some hierarchical connectivity within the output layer. The architecture is fixed here, not learned. But if you simulate this network with Oya's rule for the black connections and an anti-Hebbian rule for the red connections, you find as many principal vectors as there are output neurons, and which again we measure with a loss function. But now we have two rules, and both are parameterized in the same way as before. So here is the evolution of these rules across an optimization. Above is the rule for the black connections, and as before, you can see it goes to Oya's rule. And below is the red rule, and for this one, the Hebbian term goes to some minus something. So again, we recover the rules that we want, and this approach scales because this was a 5 by 5 network, but it succeeds in larger network, like 50 by 5. Now I move on to the last task we tried, and the spiking model. So these models are highly nonlinear, but considered difficult to tune, but they tend to be like closer to how a real brain operates. So there is a spiking neuron receiving excitatory and inhibitory inputs, and these inputs are divided into groups within which the spike trains are all drawn from the same time-varying mean. And the excitatory weights are fixed so that each group has a different influence on the membrane potential, but the inhibitory synapses are plastic. And the task is for the neuron to spike at a fixed firing rate despite these unreliable inputs. So this is a form of homeostasis, and it's a ubiquitous property observed in cortical networks. We simulate this neuron for around a minute or so, and we let the plasticity rule change the inhibitory connections. And then we measure the firing rate of the neuron at a random time after that. And the loss is simply the difference between the firing rate that we measure, R bar, to the firing rate that we want, our target, and average over several trials. The plasticity rule parameterization is now spike-based. This is the change of an inhibitory weight across time. And the first term governs the weight update when there's a presynaptic spike with this alpha term. The same for a postsynaptic spike and beta. And the last two terms are Hebbian terms. So every time there's a postsynaptic spike, how long ago was the last presynaptic spike, and update the weights accordingly. And yet the other way around for the last term. Overall, this is a parameterization that encompasses most rules found empirically. So what plasticity rule are we expecting? If we do a steady state analysis on the weights, we find a single equation linking these 6 parameters. So a priori, a big solution space. And empirically, this is the result of an example optimization. So on the left, we plot the evolution of each plasticity parameter as the loss is minimized, as you can see on the right. So we converge quickly to solutions that have a very good loss. And you can see that alpha and beta, the green and gray lines here, also converge quickly to some value. But the Hebbian terms, they seem to wiggle around without much happening to the loss. So what do we do now? What do we make of this single plasticity rule? So let's plot many of such optimization trajectories in a single plot to see if a tendency emerges. We choose to plot these trajectories in the alpha-beta plane, the 2 plasticity parameters from before, which seem to be important in the figure I showed you. And these dotted lines, they define a cone in which plausible solutions from this steady-state equation live. And importantly, this diagonal line here has only the solutions for which all the terms except alpha and beta are 0. So let's now plot the optimization trajectories, and they start from triangles and they go to the dots. And you can see that all the trajectories, like this green one, starting from the bottom left, rush to the diagonal line, aka the alpha-beta solution, and then start going slowly away from it. And they end up in one of 2 sinks. So what you see here is that the easiest way to solve the task is just through alpha and beta, so which establishes a global balance. but this is not very reliable. So the optimizer finds it can establish a detailed balance by using the Hebbian terms. And the two local minima that you see are roughly short-term plasticity in the, on the left here and regular plasticity in the middle. And what's interesting also is that in the literature, like a single rule from one of my advisor's papers actually is predicted to solve this task. It's the red star. And we show that in practice, at least all the rules work. And we're now going at the network level and adding more features to the model to test the robustness of this finding. So to summarize, we've built a pipeline to learn biologically plausible plasticity rules with black box optimization. And we've shown a proof of principle that both in rate and spiking models, this method is at least relevant and promising. And also, yeah, this finding that is challenging the current literature on inhibitory plasticity. Of course, our goal is now to apply our method to real-world problems with actual spiking networks in the inner loop and real experimental data in the loss function. So if you want to know more about it or share ideas on setup you think are interesting, so please reach out or check our preprint that has just been accepted to Neurips. So this project is the outcome of a fruitful collaboration and the support of funding bodies. So thank you all for your attention. And yeah, I'm happy to answer the questions.
Thank you, Basile, for the interesting talk. And we're well ahead of schedule. So we have time for a couple of questions. So please post your questions in the chat box. And I could then direct them to Basile if you have any questions. No questions? There's a question. If you have to define the model first before you optimize.
What? Sorry, if I have to define the model first?
So the question is, do you have to define the model first before you optimize?
Oh, can I explain the question maybe? Right, so like Oja's rule is a multiplicative rule, and then you have these other rules which are like weights times the inputs or something. So do you have to like predefine what the structure of the solution is before you optimize the parameters?
Yes. So so that's the parameterization I think you're talking about. So we choose within the parameterization what is the search space, so what kind of rules we could be looking for. But the idea is that you make this parameterization as like large and flexible as possible to be able to encompass like all kind of ideas you could be having.
Cool.
So I have another quick question if there are no more questions. So what kind of inhibitory synaptic dynamics do you model? So do you also take into account that certain inhibitory synapses could be facilitating, or all your inhibitory synapses depressing?
So right now, there is none of that explicitly in the model. This is just a conductance-based leaky integrate and fire neuron. So right now, there is no, there could be some depression or facilitation, but like through the plasticity rule, but it's not explicitly modeled. But this is something indeed that we want to get to start to include in the parameterizations, of course.
Oh, that's nice to know. Mm-hmm. So if we have no more questions, then let's thank Basile again for the nice talk. Oh, no, not yet. There's one more question. I don't know if this is quick. So someone asks if the activation function of the network, if it could affect the identification of the plasticity rules.
So I think the answer is yes, but if you like, for now in the rate network that we had, there was like the activation function was linear, so we didn't really have this problem yet. And for the spiking network, in some way, it's already predefined. So for now, we're not really playing explicitly with the activation functions, but surely it probably has an influence on what we find, of course.
Okay. So now in the interest of time,